So now let's talk about metrics for regression and classification. There are many different evaluation metrics, both for classification and regression. So here we're going to talk about some of them. So the most famous and commonly used metric for classification is the accuracy. So here we see a confusion matrix. We have the true positive, the true negative, the false positive, and the false negative cells. And how we derive this? Well, if you see here we have the true labels, we assume it's a binary classification task, and the predicted labels. So what we care about are the ones that is diagonal. So we want to predict 1 when the real value is 1, and we want to predict 0 when the true value is 0. So the accuracy is simply calculated as true positive plus true negative over all the cells. That is simply the percentage of correct predictions, which is good when the classes are relatively balanced, but multi-class problems can be tricky. Two other metrics which are better suited for imbalanced classes problems are the pair of precision and recall. These metrics come in a pair because the more we try to improve one, the worse the other becomes. So we need to have both in balance. So the precision is defined as the true positive rate of the true positive rate plus the false positive rate. It tells us that if you predicted that something is true, is 1, then how accurate would this prediction be? Recall is defined as the true positive rate over the true positive and the false negative rate. So this is basically telling us how many of the positives in our dataset the model manages to collect. So ideally, we want to capture as many of the positive cases as possible. This is recall, and then we want to have a high degree of confidence that these cases are indeed positive. This is precision. So these metrics are very often used in medicine, for example. So let's see an example of a medical case. So let's say that you're trying to predict whether someone has a particular disease. So if you have high recall and low precision, then you're going to capture most of the cases of this disease, but you won't be very certain as to whether these individuals actually have this disease. So this means that you're going to have to conduct multiple tests to figure this out, which is costly. On the other hand, if you have high precision and low recall in this problem, you might miss many individuals who actually have this disease, but when you predict that someone suffers from this particular condition, you'll be very certain in what you say. This picture here also summarizes pretty nicely what precision and recall are about. So as you understand, these two metrics, they are a trade-off, so we have to choose one or another, and we have to try and find the correct balance. And this will obviously depend on our problem. So let's move on to the F measure. The F measure is the harmonic mean of the precision and the recall. So here's a general formula for the F measure, but most often we're just using the F1 measure, and this takes values between 0 and 1, and obviously we want to have as high as a value as possible. We have the option to make some adjustments here which will give a different weight to the precision relative to the recall, but in the majority of cases the F1 measure works pretty well as it is. So it's easier to use a single measure to figure out whether a classifier works best rather than a pair of metrics. Another good metric for classification is what is called the area under the curve, AUC. So there's this concept called the receiver operating characteristic curve, and it's a plot of the true positive rate against the false positive rate for different decision thresholds of a binary classifier. So obviously, in order to use this, we need to have a classifier which can produce a threshold, and we need a binary classification problem. The perfect model will be a model that touches those lines. And the model that touches the diagonal line is a random model. So we only care for models which are in this area. If a model ever falls below this area, then it means it performs worse than random, essentially. So this plot helps us figure out the balance between the false positive rate and the true positive rate. And the area under the curve is a single metric which measures how much area the classifier captures over this part of the plot, and obviously the higher the better. So if we capture the full area here, if we get 1 in this area, then our classifier is in theory perfect. Another interesting metric for problems which are imbalanced, that is, one class might dominate the other. So maybe you have 90% of examples belonging to class A and only 10% of examples belonging to class B, is Quench kappa statistic. So Quest kappa statistic measures the percentage improvement over chance agreement. That is, if you have a multi-class classification problem or an imbalanced classes problem and you were just predicting at random, how much better does your model perform over these random guesses? So it's a metric that goes from negative to 1. Obviously, like negative values and kappa are quite rare. You might more likely see something close to 0 if your classifier is useless, because essentially 0 means no agreement. So it's very easy to use, obviously higher values of kappa being better. The challenge being that it does not have a direct easy interpretation as to how much better, let's say 0.6 is over 0.5. But then again, it's relatively easy to use because essentially most of the time you get values between 0 and 1, 1 being a hard ceiling. And so far we've talked about classification, but what about regression? So in regression, the problem is a bit different because there are many different ways to measure the deviation of the predictions from the actual values. So one of the most common ways to measure this is the root mean squared error. So the error here are the real values y against the predicted values y hat. So what we do here is we calculate this and then we square it to have a positive number. We sum them up, calculate the mean, and then we get the root. The reason we do this is because by getting the root, we can express the error in the original unit of measurement of the data points. So if, for example, we're measuring, let's say, dollars, then the root mean square error is again measured in dollars, which is a very useful property. Another way we can do this is instead of using squares and roots, we can use the absolute deviation, the absolute value here. And you can see that whether we use squares and roots or the absolute deviation, then the actual error will look different. So in the red line here, we have the mean absolute error, and the blue line, we have the root mean squared error. So you see that the root mean squared error penalizes more larger deviations and penalizes less smaller deviations. So what we choose is actually going to affect the image we convey. And also we can do things such as measure the relative absolute error, which is the actual error over a benchmark of simply predicting the mean. So this is another form of error. And there are really many different metrics, some absolute, some relative. Something else which is not depicted here, for example, is we can also estimate the error of the prediction over the actual value, for example. Yeah, there are many different metrics we can use. But in practice, the root mean squared error is the most commonly used. So if you had to go with one metric, then this would be it. And once again, you can use this to express the error in the unit of measurement of your response variable, be it dollars or something else. In regression, another very useful metric is the correlation. So why would you want to use the correlation? The thing is that it's not always easy to understand what the unit of measurements represent. So the correlation can give us a better understanding of how well the model works, irrespective of what the unit of measurement is like. So what I mean by this is that in some problems, maybe $10 is a small amount, maybe $10 is a large amount. It really depends. The correlation is a unitless metric and can tell us how well the predicted values correspond to the test data, to the ground truth. So for a good model, we would expect that if we plot the predictions against the real data, they will all fall in diagonal. So this is a very good model, and this is a worse model, however. So you see that the predictions and the real values here, they fall on a diagonal, but they're not so close to the diagonal as they should be. However, there's an issue with very biased regressors. Let's take this example. So let's say that you have a model which seems to closely follow the diagonal. However, it's off. So the gradient is very similar. However, it's off by some points. So it systematically overestimates or underestimates the true value. So in this case, there's another fix called the concordance correlation coefficient, which is stricter and can actually penalize for this bias. Because if we simply use the Pearson correlation coefficient here, it would give a higher value than the concordance correlation coefficient because it wouldn't penalize for this bias here. And obviously in regression, we can use the R-square, or otherwise the coefficient of determination. We already mentioned this, which measures the percentage of the variance explained by the model. And for multiple linear regression, I mentioned we have some adjustments such as the multiple R-squared and the adjusted R-squared. In machine learning, there's no consensus as to how to calculate R squared. So scikit-learn goes with an implementation that it's supposed to be the percentage of the variance explained, which is sometimes it's negative. So it's a metric used by scikit-learn in Python, but maybe not everyone will accept this as a valid metric. But in practice, it's used quite often. So to sum this session up, you have lots of choices in terms of how to validate your models and as to the metrics you can use. As you materialized, there's not a single recipe for all models. Yeah, so your job as a data scientist is to be able to understand what models work best for what problems and to find the right validation procedure and metrics to do that. So we're going to see some examples of different cases in the course of how we can choose the best models, how we can validate them, and you'll gain more and more experience as you work in different problems.